Here is the black body radiation spectrum, which gives the glow of hot objects at different temperatures. In 19th century, all the available theories of classical physics failed to explain this curve. But there was one unusual attempt that succeeded. In this video, starting from the basics of what is black body, we will discuss that particular attempt that opened the door of quantum physics. Before we go deeper, let us first understand what a black body is. Take a metal and heat it. First, it glows red, then yellow, and finally white as the temperature rises. Even at room temperature, it is emitting radiation, but it is in the infrared region, which is invisible to our eyes. Now, when we maintain a body at constant temperature T, it is in thermal equilibrium. So the rate of emission is equal to the rate of absorption. Or in other words, we can say the ability to radiate is proportional to ability to absorb. Now, an ideal body that can absorb all the radiation incident on the body, regardless of the frequency, that is what we call as the black body. Practically, we can make one using a hollow cavity with a tiny hole. Now, any radiation incident in that tiny hole will undergo multiple reflection and finally it will get absorbed. Now, if we maintain this body at a particular temperature, the radiation which is coming out from this tiny hole is basically the black body radiation. Here I would like to mention two notable attempts to explain the black body radiation. The first one is the Rayleigh-Jeans formula. Now, this formula was able to explain the spectrum at low frequency, but as the frequency got higher, the energy was tending to infinity. The second one is the Wien's energy distribution formula. Now, this formula worked at higher frequency, but at lower frequency, it was not matching with the experimental data. And I would like to mention here that Rayleigh-Jeans formula was derived by using the classical electromagnetic theory and statistical mechanics and had a proper theoretical foundation. But in the case of Wien's law, it was more a kind of an empirical formula rather than a fully rigorous derivation. In Rayleigh-Jeans approach, the cavity walls were treated as perfect reflectors and the electromagnetic waves inside form standing waves. And these standing waves were modeled as oscillators. Now, using the equipartition theorem, the average energy per mode was calculated and it extended to 3 dimensions, giving the Rayleigh-Jeans formula. Now, this was a proper physics-based derivation, but the problem was at high frequency, it predicted infinite energy, which is also known as the ultraviolet catastrophe. Then came Max Planck with an ingenious scheme. He wanted a formula that smoothly connects the Rayleigh-Jeans law at low frequency with the Wien's law at higher frequency. And to make it work, Planck introduced a radical assumption that the exchange of energy between the matter and the radiation is not continuous, but comes in discrete packet. And this packet of energy is proportional to the frequency, and h was just a constant to fit the black body experimental data. And finally, he gave this formula, Planck's distribution formula. And this formula perfectly fit the experimental data of black body radiation. Now, the radical assumption which he made, that is, exchange of energy is discrete, that was something new. And this opened the door of quantum physics. Planck's formula not only fit the full spectrum, but in the limits of higher and lower frequency, it reduces to the Wien's law and the Rayleigh-Jeans formula. In the low frequency limit, this term we can approximate by this expression using the expansion. And if I substitute this, we will get this expression, which is the Rayleigh-Jeans formula. And in another extreme, that is at high frequency limit, here the exponential term will dominate and we can approximate by this expression. And if I substitute, we get this formula, and this is nothing but the Wien's distribution. So this Planck's formula was no longer a patchwork, but it was a complete solution of the blackbody radiation. And that desperate fix marked the true beginning of quantum mechanics. Thank you everyone for watching this video. If you found this video helpful, don't forget to subscribe. And if you want me to cover more topics in physics, let me know in the comments.